Brilliant. If I could just ask again if you can have your microphone turned off so that we don't get any background interference. I could just hear a little bit still going. Brilliant, thank you. So welcome to today's session, all about learning times tables. So I'm just going to go through our agenda today, so what you can expect. So we're going to go through and understand the different laws of multiplication and how this can be used to help you learn or help children learn times tables. We're going to look at lots of different ways of learning times tables. We're going to look at pattern spotting within times tables and also how to problem solve within times tables. I very much want to stress that times tables, while it's a really important fluency topic and children absolutely do need to know all their times table facts, up to 12 times 12 at the end of year 4. It doesn't stop there. There is so many connections to be made within times tables that apply to other sets of learning that come up later in the curriculum. So I'm really hoping that I show you what those different connections that can be made and also the value of doing pattern spotting with times tables. Because we're not all in a room together and this is virtual, I am going to be asking, we're going to have it a little bit interactive. I'm going to be asking for you guys to be popping answers into the chat, or if you're feeling brave enough, unmuting and answering some questions as well. So the first thing I'm going to start with are the different laws of multiplication and how they can be used to help us with our times tables. So the first one I'm going to start with is the commutative law. And this is the key principle that it does not matter which order numbers are in a multiplication equation, the answer will still be the same. So that's the equivalent of 3 times 4 is the same as 4 times 3. Now, this first comes up in the national curriculum in year 2, and it builds on commutativity of addition. So 4 add 3 is the same as 3 add 4. How can that help us with our times tables? Well, as I'm sure you can see already, that if you know 3 times 4, then you also know 4 times 3. And if you were to look at a multiplication square, you can essentially halve the number of facts that it is children need to know if they have a really good understanding and grasp of the commutative law. And I've often shown this to children. I've shown them a multiplication square and said, these are all the times tables you need to know. And then I've shown them this, or just covered up half of it and said, you actually only need to know this many. And it's a real revelation for children who haven't made that link and haven't made those connections, that while they might not know their 8 times table, if they know their 3 times table and their 6 times table, then they already know some 8 times table facts. So a really important law to not only teach the children in the sense of they need to know it in addition and multiplication lessons, but also just to highlight how this can be used to understand, know and recall a great many more times table facts without having to learn more facts, if that makes sense, because they're just making connections between the ones that they already know. The second law, or the other law I'm going to talk about, is the distributive law. So this is the key principle that multiplying a number by a group of numbers added together is the same as doing each multiplication separately. And I always think that's much better explained by an image. So for example, 2 times 3 is the same as doing 2 times 1, adding 2 times 2. And you often see this when you're doing the grid method. So for example, partitioning a number, a 2-digit number into 10s and 1s, multiplying it separately and then putting it together. That's often where I first see it coming up, but it absolutely can be used to help learn your times tables. And I'm going to be talking about it more later. If you think about the first times tables that children are learning, 2, 5s and 10s, think about how tricky the 7 times table is. If children are confident with their 5s and they're confident with their 2s, they can use that to help them recall or learn or work out the 7 times table just by knowing their times tables from what they're supposed to be knowing in year 2. So the national curriculum explicitly mentions this in year 4, and it refers to when they're learning, as I said, formal multiplication, but absolutely still can be used to learn times tables. And I've actually got this picture here, I hope it's coming up big enough on the screen, of an excerpt from a Maths No Problem lesson. and it's the 3 times table. And I just want you to all have a look for a minute at the orange cubes and the red cubes. And I want you to have a think about, why do you think there are orange cubes and red cubes? What does it mean? What is that trying to show? Why would it be split up like that in a year 3 lesson about learning the 3 times table? Now, please feel free to pop it in the chat. Why do you think some cubes are orange? Why do you think some cubes are red? Maybe some of you feel confident enough to unmute, please do. So we've got someone saying they've got different values. So do you mean that the orange cubes have a different value to the red cubes? Okay. What does anyone else think? Why do you think we've got orange cubes and red cubes? Okay, so somebody is saying orange is for the tables that they know. And someone else is saying that the orange ones could be the key times tables to build on. So 4 times 3 could be double to get to 8 times 3. This is all brilliant, everyone, and thank you so much. And that is completely right. It's been split up using the distributive law, although we might not be using this language for children year 3, but that's for us, that's for knowledge for us to have as teachers, that the orange cubes, or the orange facts, if you like, are times tables that they already know. So we've got the 1 times 3, we're just going to assume that everyone knows their 1 times table, the 2 times table, the 5 times table, and then we've got the 9 times table. I'm going to talk about that in a second. So children from coming up from year 2, we're assuming that they know their 1 times table, their 2 times table, and their 5 times table. Now, the red cubes are either adding on or building on those known facts. So, for example, working out 3 times 3 is 9. Well, you already know what 2 times 3 is. You know what 1 times 3 is, so you can use that to work out 3 times 3. The same if we look at 8 times 3. You already know what 5 times 3 is. Maybe you know what 3 times 3 is. You can add them together. Same for 6 times 3. You know what 5 times 3 is, so you add that to the 1 times 3. And it is essentially splitting up the times tables facts using the distributive law, essentially, in terms of the ones that they already know and the tables that they already know. So that's a really nice visual way of how you can use knowledge of the distributive law to help you when learning times tables, or when trying to work out times tables, and stopping the old fingers just coming out all the time. That's not an efficient method. If a child doesn't know a times table, what are the other methods that we're teaching them other than just counting up using their fingers? And as I said before, the 7 times table, I'm assuming that children going into year 4 hopefully have some 2 times table knowledge and some 5 times table knowledge. Therefore, they can use that to help them work out the 7 times table, which often comes up as a tricky one. Now, other ways to know your times tables. Now, I'm going to show you this activity, which is using knowledge of the distributive law. So say you have children, year 4, year 5, maybe year 3, and they can parrot out their times table facts. They know them fluently, they don't get them wrong. That's all brilliant. But what's their understanding of the composition of times tables? Do they understand the commutative law, the distributive law? What do you make of these statements below? For A, for example, do you think that 8 times 5 is the same as 8 times 4, then add 5? Is that correct, or is that not correct? Should it be something different? What about B? Is 7 times 8 the same as 8 times 8 take away 8? I'm going to give you a minute now, and I've labelled them A, B, C, D. Can you pop in the chat once you've worked them out? Which statements do you think are true, and which statements do you think are false? And if you think they're false, how do you change it to make them true? So somebody is saying that A is false. How could you make it true then? How could you make A true? So somebody has said that A can be changed to 8 times 4, add 8, not add 5. Interesting. Yeah, so I can see lots of you saying that, and essentially you are correct. 8 times 5 is equal to 8 times 4, add 8. The mistake that has been made there, if a child were to say that this is correct, it is not, in this case, lots of 5 that you're adding, lots of 8. Because if you have 4 lots of 8 and you need 5 lots of 8, it's an 8 that you need to add. B, I can see lots of you saying it is indeed correct. 7 times 8 is equal to 8 eighths, but then you have to take away an 8 so that you only have 7 of them. So this is just a different, this is an example of how you can check for understanding of times tables using the distributive law. This is a really nice way, and Maths No Problem does have, and White Rose as well, lots of examples of these types of questions. These are really powerful questions for children that are able to just fluently reel off their times tables, but to get them thinking about it more deeply, like what does it mean? Or what do these statements mean? How do we make them correct? So really nice activities to use to build on children who are already fluent at their times tables. So now I'm going to be showing you lots of material from the NCTMD materials. Just come out because I just want to show you sort of like what they look like. So there's I've got a funny advert coming up, let's get rid of that. Too many resources to go through sort of in one go, but that's why I just wanted to show you where lots of this stuff comes from, because I'm obviously not going to be able to go through absolutely all of this. I've just picked out some key highlights, but the NCTM, these materials, they have group the times tables. So this one is when you start off, so grouping in terms of twos. This one is tens and fives. Oh, this one's not loading, what a shame. This one, if I go all the way back up to the start, this is times tables 2, 4, and 8, and the relationship between them, really important. This one, if I just go up to the top, 3, 6, and 9, and the relationship between them. 7 times table, patterns and within and across times tables. And then this last one here, the 11 and the 12 times tables. These are absolutely fantastic, these resources. I really like how they've been grouped in terms of the patterns between them. So 2 4s and 8s, 3 6s and 9s. You've got your 7s, but with patterns. And then you've got your 11s and 12s, which build on all the prior knowledge. And then you've got your starting one where they're grouping in twos. So I just really wanted to show you all some materials from there. Again, not just focusing on parroting out 144 times table facts, but looking at all the relationships between them, how to teach them. So if you have children that don't know their times tables, what is it that you're teaching them? For children that know them, what connections is it that you want them to make? So for lots more in-depth knowledge of what I'm going to show you, that's where I got them all from, and I'm happy to put these in a link after this session for you to go to for your specific year group or specific times table that you're not confident with or not familiar with in your class. So starting off with that multiplication square, like I told you, when you're starting out in year 2, year 3, I love showing children sort of a blank one first of all, and then just filling in, for example, all the zeros and the 1 times table, and just taking that fear out of it and saying, well, we all know our 1 times table. Something times 0, which should never be left out, by the way, always should be an explicit teaching point, multiplying by 0. If we fill these all in, it looks a little bit less daunting. And then the 2, 5s, and 10s, which we're going to assume they have learnt from year 2, or if they haven't, we need to go back, and they've come into year 3 with their 2, 5, and 10 knowledge. If you think about it and you look at the times table square that you've got in front of you, there aren't actually that many gaps at all. And if you use what I was saying about the commutative law earlier, there's actually even less times tables facts that children need to learn. And so I really like showing children who are a bit daunted by times tables, showing them something like this to show them that it isn't this huge insurmountable amount of work that they need to memorize, that it could be broken down even further. I'm always a fan of, and these again from the NCTM materials, showing times tables pictorially. And here we've got example of the commutative law coming up. So 4 times 10 is the same as 10 times 4. Showing timetables on a number track as well. So like skip counting on a number line or a number track, if you like. As well as splitting them up into their odds and evens counterparts. I'm going to talk a lot about the value of doing that later, but instead of just learning the timetables in order, doing them in a slightly different order, but seeing the patterns within, for example, timesing them by odd numbers, timesing them by even numbers. And then if you have a look at this one down here, where I'm sort of, I can get my pointer, this one here, the 10 times table has been grouped differently again. So we're not just doing them in order. We've looked at odds, we've looked at evens, and then now down here, we've got an even different structure. We've got 4 and 8, we've got 2 and 6, and we've probably got some random ones up here, like 7, 5, 9. But another way you could do it is 10 times 3, 10 times 6. What that's trying to get at is the patterns between the different times table facts, that 10 times 8 is double 10 times 4. 10 times 6 is double 10 times 3. So it's always really valuable, I say, showing times tables in a different order to just the standard, 1, 2, 3, 4, 5 times, but also just showing them randomly and expecting them to fluently recall. But showing them in a structured way that exemplifies a certain pattern that you want them to spot. Always worth doing, as well as just going up your times tables or doing it randomly. Lots of matching activities and lots of ticking examples that represent facts in the 10 times table. That's a really nice pictorial way into learning the 10 times table, to give them that sense of number. So seeing 10, for example, on playing cards, seeing 10 on as a 10 pence coin. And the language of grouping as well, really important. So 40 has one more group of 10 than 30. 30 has one fewer group of 10 than 40. I'm guessing that children don't often come across times tables being said in that way, but that will really help when doing those distributive facts, working out those distributive facts and whether they were true or false. If they've been exposed to times table in this way, if they've ever described the fact that 4 times 10 is one more lot of 10 than 3 times 10, it's really going to help them understand and unpick what each factor means, and help them out later on with those sorts of statements. In the NCTM materials, they have something called Dong Nao Ching, which is, I think it's from Shanghai, but I could be corrected. Essentially, it means challenge or depth or think differently. And they always have these for each times table for thinking a little bit more deeply about the question. So here we've got which expressions match this picture, explain. So there we've got a little bit of understanding of commutativity, of grouping, got a bit of the distributive law as well. And that explanation of why does this match it? Why does 4 times 3 not match this picture? Why is the 3 not in this picture? Ticking, what are products of the 10 times table? So going beyond the standard 12 times, whatever number. But what patterns from learning this times table can you utilize to help you predict other multiples of this number? So 160 or 150, they're not in the 10 times table up to 12 times 10, but can children, having understood the pattern of the 10 times table, realize that they are multiples of 10, and that, for example, 111 is not a multiple of 10? Can they explain why? Lots of these sorts of questions as well, and I love these types of questions. We're going to come across lots later. Is 12 times 10 bigger or smaller than 11 times 10? It's a nice one to start with, but then look at where it goes to. Is 12 times 10 bigger or smaller or equal to 11 times 10 add 10, etc., going through just like we did before. So again, it's deepening and stretching and applying their knowledge of times tables facts. Similarly with 5 times table, and I'm sure you as class teachers have all made the connection between the 5 times table and a clock and time. But learning your 5 times tables alongside learning about time is really recommended, because they complement each other so well. And you can essentially see a clock as a double number line with the 5 times table. So in the middle, you've got your you're going up in ones, and then on the outside, it's going up in fives. So a really nice way of presenting the 5 times table is with a double number line when looking at clock. And you'll notice, and I just put this on here to show you a similar language of groups that we've come across before. 7 groups of 5 is equal to 35. 7 times 5 is equal to 35. 5 times 7 is equal to 35. Lots of different ways of saying this times tables, including groups. Spotting patterns on 100 squares. I'm sure we've all done this, especially with the 5 and the 10 times table. It's super obvious, but equally valuable for the times tables that come later as well. There's patterns with every single times table when looking at 100 square. And once children have learnt or know more than one times table, a really nice way of getting them to pattern spot is doing these Venn diagrams. So what are multiples of 5? What are multiples of 10? What goes in the middle? And you could do this really for any of the times tables, but it is really nice to do it with the times tables that are linked and that have patterns. Oh, I just went for the wrong one. And so then we're moving on to 4s and 8s, and we're filling in the multiplication square as we go. And as you can see, every time we're doing this, the number of facts that children need to learn is actually getting smaller and smaller. So very much similar things to what I've shown you for the 5 and 10 times table. Always linking back to pictorial representations, building up the 4 times table from facts that they already know. So children who say they don't know their 4 times table, well, we're going to assume, as I said, 0 times table, which we never leave out. We know that. We know the 1 times table. And we know, hopefully at this point, the 2, 5s and 10 times table. And if you lay it out like that and get them to fill in what they know, how can you use these facts that you know to work out the missing gaps, and encourage them to do that, as opposed to just sitting there counting up in 4s. Get them to sort of reason a little bit more about how to work out the times tables, as opposed to just working them out by consistently adding 4s. So I'm going to get you guys to have a go at some of these questions. So missing number symbol problems. So I've got my little arrow here. Can you fill in the missing symbols for these this fact here, or these facts here? 9 times 4 is what? 8 times 4. And 9 times 4 is what? 8 times 4 add 4. Is it greater than, less than, or equal to? So can you guys pop it in the chat, or have a go at writing in the symbols to make those correct? So we've got 9 times 4 is greater than 8 times 4. Yep, absolutely. And then we've got 9 times 4 is equal to 8 times 4 add 4. Perfect, guys. And there's more coming in. Brilliant. Now let's have a look at this as I'm hoping I'm pronouncing this correctly. Dong Nao Ching, fill in the missing numbers. So actually now we've gone beyond the 12 times 4 table facts that children learn in class. So now we're looking at 20 times 4, or 4 times 18, 21 times 4, or 4 times 19. So just like we were doing here, when we were using the facts that we knew to work out facts that we didn't know, how can we get children to extrapolate this and apply it to this? If we know what 20 times 4 is, how do you use that to work out 21 times 4? If you know what 4 times 18 is, how do you use that to work out 4 times 19? And same here, if you know 15 times 4, how do you use it to work out 14 times 4? And same again here. And you'll notice the pattern here with these first 2 sets of questions, it was getting bigger by 4 each time, because you were adding 1 more 4. And with these ones down here, it was getting smaller by 4 each time. So these are really carefully constructed questions to reveal the patterns within the time, in this case, the 4 times table, and get children to apply the skill that they were probably doing when just learning the 4 times table, now that they're fluent with the 4 times table, they can recite it all. Now use that to work out other 4 times table facts beyond the 12 times 4. And so I'm now going to have a look at 3, 6, and 9 times tables. So looking at the fact that the 9 times table is essentially triple the 3 times table, and making that really, really explicit. So if you know what 5 times 3 is, you know what 5 times 9 is, because you just have to triple it. And you can see here the way that these times tables facts have been presented. They've been presented with the 3 times table, first of all, because we're assuming at this point that children know their 3 times table. And then you've got the 9 times table fact underneath. And in exactly the same way we were doing before, the idea is that they use this known fact that they already know to work out the unknown fact, and really embedding each time that they do this, that to work out the 9 times table, it is triple what the 3 times table fact is. Lots more of these types of questions, filling in missing symbols. And now we've got a true or false question, which again, I'm going to get you to do. We'll just call them, I don't know, A and then B. 6 times 3 add 9 equals 7 times 3. True or false? Or 6 times 9 add 3 is equal to 7 times 9. Is that true or false? I'll give you guys a minute to work that out and pop it into the chat. So a lot of you I'm seeing are saying false. If you think it's false, can you write what would be one correction or a way of correcting the statement so that it is true? Yes, lots of people saying false. I completely agree. So how do you make it true? So we've got one example. 6 times 3 add 3 equals 7 times 3, not add 9. And lots of you are coming in with that. So, yeah, you're completely right. These true or false questions, again, a really nice way of getting you to think about these times table facts and use what you know about the distributive law, about the composition of times table facts, about what each of the different factors represents to make these statements correct. I would also say, and I haven't mentioned at this point, using physical resources would greatly aid this. So making a 6 times 3 array, making a 7 times 3 array, seeing what the difference was between them, seeing what it was that you had to add or take away. So I'm going to look at the 7 times table now, which I have talked about. It's really similar again. Knowing, for example, that 10 times 7 is equal to 9 times 7, add the 7, just like we were looking at. Lots of filling in the missing symbols for these different times table facts, getting them to compare them. Always starting off with something that hopefully is something really easy for the children to grasp. 9 times 7, or 9 groups of 7, or 9 multiplied by 7. Hopefully they see is always going to be bigger than 8 times 7 or 8 groups of 7, because you just have more groups of that number. And then using that and building on that knowledge when it gets more complicated, using addition and then using subtraction as well. I'm going to look at very briefly the 11 and the 12 times table. Now, the 11 and the 12 times table, it often lends itself and comes up when you are doing, for example, the grid method, because you are often having to split up numbers into 10s and 1s. And so the 12 times table, and to some extent the 11 times table, really lends itself to that. And actually, before I teach the grid method, I often use 12 times tables facts to show this method, because hopefully it's something the children can relate to, they understand. And then underneath we've got the workings here, and this is what it would look like as an array being split up into 10s and 1s. And again, just like I mentioned with the 7 times table being made up of the 5 times table and the 2 times table, the 12 times table is made up of the 10 times table and the 2 times table. Now, very similarly, For children to work out the 12 times table, can they first of all put in their known facts, the ones that they already know, and use it to work out the ones that they don't know? Now, a dong now ching, going deeper, or a challenge for the 12 times table. Is this true or false? Star divided by 12 equals diamond because star times 12 equals diamond. Is that true or is that false? Now, while you guys are working it out and putting it in the chat what you think, what's really clever about this is it's actually not using numbers. There's actually no calculation involved with this times table fact at all. It is purely focusing on, do children understand the relationship in this sentence? Is this true? Is this false? No matter what number I put in as the star, no matter what number I put in as the diamond, does this work? So I'll give you guys a minute to think about whether that's true or false or not. No one seems sure of this one. So let's add some numbers. Let's attach some numbers. So what if, oh, they're coming in now. What if the star, for example, was worth 120? So it would be 120 divided by 12 equals 10. So that means the diamond's worth 10. So therefore, what this statement is saying is 120 times 12 equals 10. Is that true? Is that false? It is false. And I can see some examples coming in have used 8 times 12 equals 96. That's absolutely fine as well. So what's really nice about this, as I said, is that there's no numbers involved. It actually doesn't use a times table fact. And actually, this is looking at the commutativity of multiplication and division, and the fact that you cannot, that division is not commutative, which is obviously helpful when you're learning your division facts as well. So a really nice different way, and you can apply this to any times table. To look at times table patterns and times table facts, is replace some of the numbers with symbols or with anything you like, so that they don't have to calculate, but they have to look really deeply at the maths. I just wanted to show you again, lots of missing, lots of greater than or less than. And then what's really nice here is the different possibilities. So for example, in these questions here, 6 times 12 is greater than something times 12 add something times 12. What are all the different possibilities you can put in there? What is 6 times 12 always going to be greater than when you're working with times table facts? So I can think of an example. 6 times 12 is greater than 1 times 12 add 1 times 12. That's definitely going to be bigger. But if I started saying something like 6 times 12 is greater than 5 times 12 add 7 times 12, that's not correct. And what's really nice for children to do with these statements is work out the parameters. So what's the lowest I could have? What is the highest I could have? And what are all the different variants in between? I just wanted to show you, we're not going to do this, but I just wanted to show you that lots of these things are out there. So matching stories with times table expressions. Again, getting children to put times tables back into context, getting them to use all of that knowledge of just sort of, parroting out fluency facts, but applying it in a different context. I now want to look at balancing equations. And if we were all in a room together, which unfortunately we're not, I would be making this array out of cubes. So I show you 8 times 4, and essentially I would break it in the middle and put one set of cubes or apples or whatever on top of each other to show that 8 times 4 is equivalent to 16 times 2. And the same again with these times table facts. As well as understanding commutativity as a helpful tool for learning times table facts, understanding balancing equation helps with times table facts as well. For example, knowing that 6 times 4 is going to be the same as 3 times 8. Because if I had it physically in front of me, if I had my 6 lot of cubes or my 4 lot of cubes, if I halved the 6 and moved it over here, that means I'm doubling the 4. So 6 times 4 is equal to 3 times 8. And the same here as well. 12 times 2 is the same as 6 times 4. 3 times 10 is the same as 6 times 5, etc., etc. And then more examples down here. So I think this is as valuable as commutativity, learning this skill of being able to double and half factors and using that to help them work out times table facts. And just as a little side note, although this session is about times tables, this is really useful when you come on to learning decimals if children have grasped this concept. For example, doing 1.5 times 4, don't need to do it with the grid method or the formal method or make it 10 times bigger. Just double 1.5 to make it 3, half 4 to make it 2, and 1.5 times 2 is the same as 2 times 2. And if children can see that, it's really powerful. So that's just one way of applying this knowledge from times tables into other areas of maths. And it comes up in the PD materials because of course it does. So the relationship here, we've got the relationship between the 8 and the 4 times table, that this is half, this is double, and really nice sort of pictorial ways of representing. Here we've got the 2 times table, 4 times table, and the 8 times table as well. So it's really worth going over those facts once they've learnt the times tables, making lots of links between those facts and showing them all the relationships. And then obviously, as we talked about before, the 9 times table being triple the 3 times table. And now I want to show you practical ways of looking at the times tables. You might not use this activity to work out the times tables, but this is a really nice practical way of looking at patterns within times tables and pattern spotting. And I'm just sorry that we can't all do this in a room together. So you get 100 square and you get out your Unifix cubes. And you have 12 of each colour. You have 12 white, 12 red, 12 green, etc. And each one of those cubes is going to represent your times table facts. So one is white, quite handily, one is white because one times table is every number, so white background, we don't have to worry about that. So I'm going to put, and I'm sorry I can't do this in real life, but I'm going to put my 12 red cubes to represent my 2 times table on my 100 square, which means I'm going to have a red cube on 2, a red cube on 4, a red cube on 6, a red cube on 8, etc., etc. And we're going to run out at 24. And then I'm going to do the same with my 3 times table. And if some of them overlap, I'm going to start stacking them. So I'm going to put my green cube on my 3, a green cube on my 6, a green cube on my 9, a green cube on my 12 on top of the red cube, etc. I'm going to go forth and I'm going to do that for every single times table. Now, when you look at times tables like this, all stacked together on 100 square, I'm just sorry I can't show you or do it, but the amount of patterns you can spot is just phenomenal. There are some numbers that have so many cubes on them because they have so many factors. For example, 24, loads of cubes. And inadvertently and indirectly, what are you teaching them through doing this activity that's not related to the times table facts? Well, you're teaching them about prime numbers because there's going to be squares that don't have any cubes on them whatsoever. 7, other than the 1 times 7, no other cubes on it. 11 is going to have no other cubes on it. 17 isn't going to have any cubes on it at all. There's no other factors of 17 other than 1 and 17. So it's really nice to put times table facts in context of other types of number and in context of where they are on the times table sort of fact system. You can do this activity where you keep going. So for example, you put cubes on every single 2 times table fact and you fill up the whole, it would essentially just be a long line of red on the 2s, 4s, 6 and 8s. You can do that, but it is just nice to do just up to the 12 times 12, because also what you will spot is that the vast majority of times table facts come in this half of the 100 square. There's very few that come up down here. And that's a really nice discussion point. Why do you have so many of the times table facts under 50? So many more than this half of the 100 square. Really nice discussions to be had from that and why that is the case. And then you can also do this kind of an activity. If you've stacked your cubes on the 100 square, well, what number could this be? So we've got a white cube, kind of a cop-out because they all do. We've got a red cube and a yellow cube. So let's do some reasoning now. What numbers do you think that could be? Let's have a look at our 100 square with our cubes on. you'll have a look that red is the 2 times table and yellow is the 5 times table. So it could be, hopefully this is the pattern that they spot, it could be 10, could be 20, could be 30, could be 40, could be 50. Oh, what do we spot about those numbers? What about cubes that have, squares that have a red cube, a yellow cube, and a purple cube? So now we're looking at what numbers are in the 2 times table, the 5 times table, but also the 6 times table. Are there many of them? And you can just mix this up as much as you want. What about the 3 times table, the 5 times table, and the 7 times table? So it's a really nice way to reason about times tables without actually showing them numbers. And I'm only sorry that we can't all do this together. But that's a really nice practical activity to do. And there are lots of different patterns and conjectures to spot from doing that. Now, I briefly went over this before, but the power of showing times tables in different orders that are non-standard. So here on the left, I've just got the 5 times table, and I've just gone up from 1 times 5 all the way up to 10 times 5. And then in set B, I've got odd numbers times 5 on the left. And is that right? Yes. And then even numbers times 5 on the right. Now, what generalizations can you make from doing the 5 times table in these different ways? What connections do the order of the questions bring attention to? And this is just another way of looking at it, 5 times an odd number versus 5 times an even number. So I'm going to have to tell you, because unfortunately we're not together, but 5 times an odd number will always end in 5. And 5 times an even number will always end in 0. And I'm just going to give you half a minute to look at this question from White Rose. And can you think, or can you tell me, why is this important that they're making these connections earlier on? I'll just let you read this question. So Jen and Max each have 5-digit cards. Max arranges his cards to make a 3-digit and a 2-digit number. He multiplies his numbers and his answer ends in 5. What could the 3-digit and the 2-digit number be? I cannot tell you how many children I have seen that just do this with trial and error, but they can also fluently do a 144 test. They could parrot out their 5 times table. They could parrot out all their times tables facts. And then they see this question and it's just complete trial and error. And there's no reasoning that happens. There's no connections that are made. There's no links that are made. But how much longer do you think it's going to take to randomly find a 3-digit and a 2-digit number and make sure the number ends in 5? And this is, I think it's a year 5 or a year 6 question. So I just, again, wanted to show you the power of learning patterns in times tables, as well as just learning them verbatim. And think about all the other connections you can make. Starting a lesson or having an investigation lesson with this. Which of these are false and which of these are true? Is an even times an even always an even? Is an odd times an odd always an even? Is it more a case of sometimes always never, or is it true and false? Really powerful stuff. And even I had to think about this when I was looking at these reasoning questions. So again, more connections to be made. And then what about this? Leo the Lion, or whoever you want, says that he only needs to know the multiplication tables of 2, 3, 5, and 10 to help find facts for all the multiplication tables. Is that correct? Is that incorrect? Can you use less times tables? So what is the minimum number of times table facts that you need to know in order to work out all of them? That is such a powerful activity to do, and really powerful for children who both know their times tables because it gets them to think deeply about it. But if they don't know their times tables, you're giving them strategies to help work them out, to help see the patterns, that it does not just involve counting up on their fingers. I want to show you another type of activity you can do, showing them a blank multiplication table. And I've missed out times 0, which is bad of me. Never miss out times 0. And what I did was I just cut out bits of the multiplication table and took out some of the numbers. I'll give you a minute. Unfortunately, we can't do this practically, but where does the red square go? Where does the blue square go? And where does the green square go? If you're able to explain in the chat where you think they go, please do. I'll just give you a minute to look at them. Some of them are harder than others. Actually, I'll come out to move it. So if I was to do this with children, I was to model this blue one here, I'd say we've got 30 as a times table fact. So, sorry, as a times table, what facts do we know, or what factors are there of 30? And you might say 5 times 6. So I say, okay, let's pop it in 5 times 6. Does that work with everything else? Is 3 times 6 24? No. Is 4 times 7 35? No. So that's not correct. So you need to come up with a different times table fact for 30. And maybe you would say 10 times 3. So let's try that. Let's put 30 in 10 times 3. Is 8 times 5 24? No. Is 9 times 6 35? No, so that doesn't work. So you need to come up with a different times table fact. So let's try now 6 times 5. Did we do that one? No, I don't think we did that one. So I've got 6 times 5 is 30. Is 4 times 6 24? Yes. Is 5 times 7 35? Yes. So it's a really nice way of getting children to think about factors and think about different times table facts that make the same multiple. So we've got our number 30, and it's a different way of looking at it. Instead of just giving them endless times table facts, give them the number, as we've done here, and get them to generate the times table facts that make that number. And doing it in this form of an activity, really nice. And you can see why I've sort of taken out some of the numbers. This green one was so difficult, and you can make it as tricky or as easy as you like, but it's like the inverse of learning times tables is looking at the fact first and getting them to generate the times tables and then see what makes it work. And because you heard what I was doing so many times tables because I was constantly having to think, does this times table fact work with this factor? No. Does this times table fact work with this factor? No. So it's a really rich, deep activity, which I really recommend. And it's really easy to do because you just print off a blank multiplication table, and you can just take snapshots of a multiplication table, put some white squares over some of them, and that's it. It's done. No more thought needed than that. You've also got different ways of looking at tables. So, for example, what are the missing numbers? So how this works is you would have 5 times 6, the answer would go here. 3 times 9, the answer would go here. And then you'd also do it going down. So 5 times 3, the answer would go here. 6 times 9, the answer would go here. So that's just like the standard, how it works. But then look at what happens when you start giving some of the products and taking away some of the factors. Something times 6 is 42, but that same factor is also got to multiply by 3 to make 21. So again, we're deepening knowledge of times tables. We're having to go through a lot of different facts, or a lot of trial and error, if you like, or using those patterns and spotting the connections to come up with what that number is going to be. And then look at this one here, or this one here, the ones on the bottom. You're just giving the product, and you've got to work out what times table fact makes 56, but then that also has to multiply with something here to make 35, and then that number here has to multiply with that to make 60. Again, really nice way of deepening, understanding, and trying out different ways of learning your times tables and making those connections, and lots of trial and error, and lots of having to try out different times table facts as well. For the younger children, or older children if you like, but another way of presenting reasoning questions with times tables. Which has more legs, 8 dogs or 4 spiders? Might look like a word problem, and it is essentially, but it's also times table facts is 8 times 4 or 4 times 8. Which one has more, which one's less, or in this case equal to? Which have more sides, 9 hexagons or 7 octagons? Which is longer, 4 blue, sorry, that should say blue, blue Cuisenaire rods or 7 yellow Cuisenaire rods? Not only is it nice to get children to answer these kinds of questions, but get them to generate them as well. And they love doing that kind of stuff. What do you know of that has 7 legs or 7 sides or 7, I don't know, whatever you want. And you could give them different parameters. So I want you to make it equal to. So with that first one, 8 dogs and 4 spiders, what if I wanted the number of legs on spiders to be more than the number of legs on the dogs? How do I change it? What numbers can I make different? So that's a really nice way of putting in reasoning with times tables. Another way of looking at times tables practically, showing them a shape, for example, this, and saying, my whole shape here that I've made with my Unifix is worth 40. The whole thing is worth 40. So what is the value of the orange cube? And what is the value of the blue cube? I did have in my plan for this session that you would be doing this. That's what that symbol means, but I'm so afraid that we're going to run out of time. But I will give you 2 minutes. That's not long. Can you work out what a potential value for the orange cube would be? And what's a potential value for the blue cube? Let's see if anyone gets it. And essentially what you're doing is 2 times something and 4 times something equals 40 when you add them together. What could it be? So we've got one possible answer. So the orange could be 10 and the blue 5. So if the orange was 10, it would be 2 times 10 equals 20. And then the blue, if it was 5, it would be 4 times 5 equals 20. And you have got your value of 40. So well done, whoever said that. 2 times 10 add 4 times 5 is equal to 40, is essentially what that is showing. And you can play around with this kind of structure as much as you want. You can change the value, you can change the shape, but essentially you're getting them to generate times table facts that can go together to make a certain target number. And you'll notice that the number of blue cubes was double the number of orange cubes. And you'll notice that number 10 is double the number 5. Lots of patterns to be made there as well. I'm just going to show you this last contextual problem from the NCTM. A class of children can sit around tables in 8s or in 4s. If they sit around tables in 4s, they need 6 tables. How many tables would they need if they sit in 8s? So I'm not, you're probably pleased to hear, going to make you do that, but that's a really nice practical problem that you can do with children in classrooms. I'm going to say COVID permitting, maybe want to put for summer term, maybe when things are a bit more normal. But that's a really nice practical way of getting children to problem solve with times tables, thinking about the number of children around the number of tables. And then you've got a bit of an extension here. So now I'm telling you that there are 32 children in a class. So how many children will be needed if each table can seat 4? And how many tables will be needed if each table can seat 8? And they can make this with the cubes. They can make up their own number of children in a class, own number of tables, as long as they're equal, very open-ended. So I'm going to finish there and just go over what we've covered. So we have covered how the commutative and distributive law can be used to learn times tables, how learning times tables in sequence is really valuable and important activity to help you learn times tables facts, and lots of different activities to support understanding, from Venn diagrams to matching to more than statements to colouring of factors. We've looked at pattern spotting within times tables, and we've also looked at problem solving and reasoning with times tables as well. I'm only sorry that we couldn't do this all a bit more together in a room, but unfortunately that's the situation that we're in now. I would love if for the last 5 minutes, if you could fill in an evaluation form, because it